All right, everyone. Good morning. I guess we had a little bit of a slow start, but that's not an issue at all. So today the goal is going to be to, just review what we talked about last class about variable rate nitrogen management. Finish this lecture here and then actually start an exercise that we're going to be applying what we learn in lecture to an actual real data set. I'm going to go quickly through these first slides here, which are the ones that we have already covered, just to refresh your mind of what we've already talked about. We started talking about spatial variability and why variable rate input technology can be helpful to address that spatial variability. In this case, we have an example of soil pH where we could be treating this field with variable rate lime application, and then a crop vigor map in the form of green NDVI, and just looking at how the crop is really responding differently across this field. And how can we address that and apply some input, in our case later is going to be nitrogen, according to how well or how poorly the crop is doing in different places of the field. We talked about difference between a stable nutrient and unstable nutrient. So a stable nutrient would be something that you can apply or treat this year, and it will expect for that effect to linger at least for that growing season, but potentially for more growing seasons as well. So that would be, we talked about phosphorus, potassium, treating pH, even though pH is not a nutrient, but is also something we can treat variably. So pH would also be a good example here. And unstable nutrients are things that you apply today, and on a very dramatic note, tomorrow we may not have it, right? And one example of that is nitrogen. And the case for that is because nitrogen is so dynamic and undergoes so many reactions once it is applied to the soil, and it can be lost through different pathways as well. So it makes it a very dynamic nutrient, and that makes it difficult to manage properly. So we talked a little bit about nitrogen losses, also how nitrogen is one of the most limiting nutrient factors to yield. And at the same time, the amount that we need of nitrogen within a field to maximize return varies greatly. So there's no way we can do a test on a farmer's field that we can do multiple rates in multiple places just so we can learn what's the best rate to apply at that place. So it's just, it's a very complex nutrient to manage, especially to manage sustainably and profitably. With that, we talked about the three variable rate nitrogen components that include sensor, algorithm, and VER equipment. We did go through the sensor and algorithm parts. So on the sensor, we talked about three main ones, one being active and proximal, which is mounted on a boom. So it's really close to the plants, and the way it works is that as that sprayer is moving through the field, it is measuring crop reflectance, using that information on an algorithm to create a rate and apply that rate right there. So it's sensing and applying almost instantaneously. Whereas with passive sensors coming from both UAV or satellite, you do have to have that data collection first to process that data, create an application map, which is what we're going to be doing today. And then you feed that into a VR equipment to apply. So it's sensing and application are done separately for the passive sensors, whereas with the active sensor, they're done on the same pass. Then we talked about how can we use sensor data to relate to crops and how that information is useful to derive a nitrogen stress and after that a rate. So this is the electromagnetic spectrum. So we have the three bands there, blue, green, and red. We have the red edge and the infrared. We talked about how different sensors may have different bands, and they may call a given band being an average of different wavelengths. So just to be aware of that. And depending on what band we have, that will determine what vegetation index we can calculate. Then we went through this example here to make that connection between crop health or perhaps vigor and how that relates to remote sensing data. So we looked at the first leaf that's very healthy and vigorous, and the last leaf that is very yellow and sad looking. And then we just look at the reflectance profile of those two leaves. And we were able to then understand, the differences as far as the yellow leaf is absorbing less, which means it's reflecting more. So here we're showing reflectance, right? So if it absorbs less, it is reflecting more of that light on the visible spectrum, especially on the green and red bands. And that's because it doesn't have as many pigments to absorb that radiation and use that for photosynthesis. Whereas a healthy leaf has lots of pigments to absorb in the visible range, and it does that absorption, so it reflects less because of that, and uses that energy to do photosynthesis, to grow, to develop, and in the end to produce a high yielding crop, if we want to think that way. And then on the other hand, the near infrared is the opposite. So a very healthy plant reflects a lot on the near infrared, and a stressed plant reflects less. So then we can connect those and calculate vegetation indices. We talked about 3 here: NDVI, green NDVI, and NDRE. If you ever work with imagery in agriculture, you will for sure run into at least NDVI. And I do want to call your attention here because NDVI, as we already talked about, saturates. The red band saturates, meaning that NDVI, after a certain level of crop biomass, NDVI cannot differentiate anymore between good and really good. It can differentiate between bad and good, but not between good and really good. Whereas green NDVI and NDRE bring back that sensitivity, I guess, by replacing the red band with either green or red edge. So just to keep that in mind as you work in your career with remote sensing. Then we just went through an example of calculating NDVI for these 2 examples here, these 2 leaves. We were able to plug in the numbers and find that the actual dark green leaf had a pretty high NDVI and the yellow leaf had a pretty low. NDVI in general ranges from -1 to 1, even though when we're talking about vegetation, you would expect to see values between 0 and 1. So a lower value, of course, means lower vigor, and a higher value means a higher vigor. Yeah.
You see that they were like this.
Say that again.
Like have like lower difference.
So what was the first word I'm missing? Yellow leaves. Yes. So yellow leaves, they're gonna have higher reflectance because they have lower absorption, right? So the light hits it, and because it doesn't have the pigment. So the question was if a yellow leaf has more or less reflectance. And I guess also depends. So let's just go back to that and see that again. So the yellow leaf here is, so it's still absorbed or still reflecting similar amounts to healthy leaves in the blue range. So that's the 400 to 500 is the blue. And then the next one is the green. So 500 to 600 is green. And then 600 to 700 is red. So we see that on the green and red bands, the yellow leaf is reflecting more, which means it's absorbing less. And the reason why it's absorbing less is because it has less pigments like chlorophyll to absorb, right? So chlorophyll absorbs radiation, especially in the visible spectrum, and uses that to run photosynthesis. So if a leaf is stressed and is yellow looking, it doesn't, so chlorophyll is what makes plants green, right? So if it doesn't have chlorophyll, then it just doesn't have all the capacity to absorb energy to do photosynthesis. So the plant looks yellow, and also because it's not absorbing as much, it means it is reflecting more on the visible range. And then on the near infrared is the opposite. So a healthy plant, you can kind of think of like, so near infrared reaches the plant and it interacts with the mesophyll of the leaf. And the healthier that mesophyll is, the more it reflects back on the near infrared range, right? So a very healthy plant is going to reflect more on the near infrared, and a stressed plant, especially if the leaf is either stressed or damaged, or just there is not enough biomass overall in that canopy, it's going to reflect less near infrared, which is what we can see here as well, right? So on the near infrared, the healthy plants are reflecting more, and the stressed plants are reflecting less on the near infrared.
So the opposite.
It's kind of the opposite if you're thinking of the visible and the near infrared, right? So the visible, you want less reflectance because that means it is absorbing more, it's running photosynthesis with that. And on the near infrared, the more the better. So it's kind of like, if you think like of a healthy plant, it's gonna reflect very little on the visible and a lot on the near infrared. All right, so I'm just gonna skip over here since we already talked about it. Then we start talking about algorithm, right? So there are different ways of categorizing algorithms for variable rate nitrogen. One of them is to categorize based on how they were developed. So algorithms that were developed with a specific vegetation index can be very good for that vegetation index and normally for the state where they were developed, but they're not as well, they don't generalize well to other regions. Whereas vegetation, so algorithms that were not developed using a specific vegetation index, they actually are more flexible and can adapt more to different regions from where they were developed. So here we showed an example of two vegetation index specific algorithms, the one from Missouri, the one from Oklahoma. We can see here how NDVI changes, how that is changing, how much rate of nitrogen is being recommended. And this was developed for NDVI, right? NDVI is what we have on the x-axis here. So we talked about, what if I have a different vegetation index? So let's say you go to your cornfield and you have high biomass where NDVI is not going to do a good job, but you do have on that sensor that you used, you also have the green band. So we may say, well, let's use green NDVI instead of NDVI. And then you come here, well, this algorithm doesn't really work with green NDVI because it was not developed for that, right? So that is one of the limitations if you do use a different algorithm. And then here we just showed how NDVI saturates. So when we think of leaf area index, so here leaf area index values above 3, we start seeing this plateauing here of NDVI. So it is becoming insensitive to LAIs of 3 and greater, right? So it cannot tell the difference. And really in corn, cotton, most of the row crops, we do have more than LAI of 3 after a certain point in the growing season, right? So this is a limitation that NDVI is going to have pretty much for any row crop that we work with. Also, what if that relationship between, let's say, NDVI and N rate was created for a specific growth stage of that crop? So let's say in corn, if the studies were done at V6, which is when the corn has 6 fully developed leaves, then if you need to apply at, let's say, a V8 or V10 or V12, does that algorithm is still valid? Probably not. So that is also a limitation of that type of algorithm. We went through that in this slide here. And also one limitation that is not necessarily related to the algorithm itself, but on this picture here, we talked already about that we have all these plots that look different to us. Their difference is due to different hybrids. So this is a corn variety trial or hybrid trial. And the difference in coloration here is all because of variety or hybrid. And, we really wish that the differences were due to nitrogen because then we can treat that, right? We don't want to treat this and say, oh, this is nitrogen stress, let's go ahead and treat it differently with variable rate if that difference is not coming from nitrogen stress, right? Where in this case it's not. So we need a way to account for that as well. So I think this is where we stopped. So this is going to be new content for today. And I do want to ask you to be very attentive to these slides because we're going to be doing this in the exercise that follows this lecture. And so if you understand what we're talking about here in the lecture, it's going to help you to understand what we're doing in the exercise as well.
Sorry, Dr. Bas.
Yes.
I don't understand the limitation.
So we have, there are different limitations, but the ones that I brought in here were, so let's say if we are using, let me just go back a few slides. So just we can quickly go through them again. So if it is an algorithm that had derived the relationship between a specific vegetation index and nitrogen rate, there are some limitations there, which is the case here, right? So we do see that both the Missouri and Oklahoma algorithms are relating NDVI to nitrogen rate. So if NDVI is 0.4, is going to apply, let's say, 50 pounds of nitrogen, right? So that limitation right there is what I'm talking about. So, if you think of it again, this algorithm was probably developed, well, it was developed with NDVI. So if you do have to use a different vegetation index, this algorithm is basically not valid anymore. You need other study, you need another algorithm for a different vegetation index, right? Which may or may not exist. The other limitation is that these algorithms here are normally developed for a specific growth stage. So let's say we do a whole bunch of field trials where we have different nitrogen rates and we go at V6 and we derive this relationship here. So V6 being a growth stage of corn. What happens then if you're going to apply a V10? So maybe like a week or two after the timing of when the algorithm was developed for. Is that still valid? Maybe not, right? But we don't know if you don't have that algorithm. So that would be the second limitation. And the third limitation is, what if the difference in crop on the way the crop looks is not related to nitrogen, right? So I guess I just want to really stress this point. For us to use any variable rate nitrogen algorithm, regardless of what type it is, we have to assume that the stress on the field is predominantly coming from nitrogen stress, right? So nitrogen deficiency. If that deficiency is water, is other nutrient, is perhaps a pest, or anything else that could be affecting that crop, applying variable rate nitrogen is not going to help. Is that because that's not what the sensor is seeing, right? You're seeing a different stress, not nitrogen. So that's just one thing to keep in mind when we're doing this. And in this case here, I'm just showing you that, of course, we have an extreme case on this picture that is a hybrid trial for corn. So we may have, I don't know how many different hybrids in this picture, but what if a grower for some reason is planting a couple or a few different hybrids in their own field, right? And then you take an image of that field and you see different coloration because of hybrids. We don't want to treat them, we don't want to assume that that field looks different because of nitrogen stress when that may be a hybrid difference that is causing the way that they look different on the image. So some of those things we're going to address using a different algorithm that's not vegetation index specific. And some of those things we're going to address using something that's called sufficiency index, which I'm going to tell you in the next slide. Does that help?
So it means for doing any application of nitrogen, I have to check the water stress index.
I mean, water could be one of the stressors, right? But not necessarily the only one. I guess the main thing is, so let's say with talking about row crops, which is my experience. So in corn, if you treated your soil for any nutrients that may be lacking, so phosphorus, potassium, pH is at a good level, if it requires other nutrients, if you have already covered all your bases as far as applying nutrients to be at the minimum level for optimal yield, and let's say if it is a field that's irrigated, and at least at the timing of nitrogen application, you're not expecting to have a lot of weed pressure, insect pressure, disease pressure. It's a good guess that if there is stress, it's going to be nitrogen related, especially in corn. Of course, you still have to go out there, you still have to check, you still have to make sure that's the case. And if that is the case, then you can apply what we're going to be doing here to apply nitrogen variably in space. But again, if the major stress that you're seeing at time of application is not nitrogen related, then a sensor is not going to help, right? Because you're still going to be trying to relate those differences to a nitrogen rate where maybe nitrogen is not the limiting factor. Maybe it is water stress. And then applying nitrogen variably is going to be confounded with that water stress. Yeah, so I guess in irrigated systems, this is a lot easier because it's a lot simpler for you to make that connection between, okay, I know water is not the stressor. I've covered my bases for nutrients. I know there's not a lot of weed, insect, pest pressure right now. So it's a good guess that nitrogen is going to be the limiting factor then.
So if you don't have an history, let's say, of the farm, and they have been doing something like consultants, it means you have to trace all those back, possibly using the technology, right?
Trace what back? Sorry, I didn't.
Trace all those indices which maybe you could just trace before doing any application.
I mean, you can, right? So let's say if you have a sensor that gives you some information about water stress, you can use that information as well to at least understand if there's water stress, right? And things can get more complicated. So there are some sensors that have enough bands that you can calculate both a crop vigor stress, but also a crop water stress. We're not going to be talking about that here today, but that's something that you can also do with sensors, right?
So that is the limitation for the so we're gonna make it up with the non-sustainable.
Yeah, so that's what we're going to see. A couple of things next here that are going to help us solve that. Yeah. All right, great questions. Okay, so here's one very important piece of information that helps us to normalize the signal and at least try to ensure that we're applying nitrogen based on nitrogen stress only, right? So let's say if you go to a field and you see stress, like some places are more stressed than others, and you use a sensor that will tell you that there is that stress difference. But then how can we really how can we understand and say like, oh, this part of the field here is really healthy looking. I wish everything else was looking this way. This is how I wish my crop would look like as far as crop vigor and as far as that's impacted by nitrogen. One way to do that is to use this concept of a high nitrogen reference. So let's say this is done both on research, but also on farms that are trying to implement variable rate nitrogen, where the farmer goes and lays out a strip across the field that they over apply nitrogen. And this is corn, right? So given that's corn, over applying nitrogen in corn is not going to hurt yield, at least not to the extent that we're talking about here. It may not be the same for cotton. Anyways, we're talking about corn. I don't want to divert into that direction. I just wanted to make that comment. So let's say the farmer goes to the field and applies, let's say 300 pounds of N per acre on that high nitrogen strip. When it comes time to variable rate application, they do use some sensors. So let's say we're going to be using UV imagery, and they can see that very healthy, vigorous strip on their field. And they're going to say, that is my reference. That's how I want my crop to look like. And then they take the vegetation index of the remaining of the field and relativize to that reference. And then that relativized number is what they use in the algorithm. So I guess two important things here. One is to have a high nitrogen reference. The other thing is to relativize. So relativize here is what we call the sufficiency index. So let's say this part of my field here is where I do want to apply nitrogen variably. And this other side here is my high nitrogen strip where I over apply nitrogen to make sure nitrogen was not limiting there. Then to calculate the sufficiency index, we basically divide the field VI. So in this case here, I mean, VI could be any VI. It doesn't have to be NDVI. It's just vegetation index. Let's say in this example here, for this strip that I do want to apply variable rate nitrogen, I go there and I measure some vegetation index, whatever it is, and it comes back as 0.35. I go and measure the same for my strip, my high nitrogen reference strip, and is 0.61. So to calculate the sufficiency index, we basically divide the field VI by the reference VI and then get this number that is a relativized, right? So now I know how far back is my field related to my reference and use that information to then input into an algorithm to give a rate.
Dr. Masters.
Yes.
So wouldn't the application of high nitrogen might have any negative effect on the crop that we are trying to take as a reference?
So that's a great question. So with corn, normally it doesn't, at least not to the crop, right? I mean, you may have more environmental losses, which is something that we also want to avoid. But normally the crop doesn't suffer from that higher rate, at least not the rates we're talking about, right? So with corn, you have to apply a very, very high rate, maybe, I don't know, 500, 600, 800 pounds of N per acre for it to really start showing stress. But the ranges that we're talking about here between like 250 and 300 pounds of N per acre do not hurt corn. Now, on the other hand, if we talk about cotton, that may be a different story, right? So cotton response is more sensitive to over application of nitrogen than corn is. So maybe for cotton, this would not work as the way that I'm explaining, but
So how can we find out the reference? I mean, if it is really sensitive to the over application of nitrogen.
I mean, just do research, right? I mean, in corn, we know that like it has a long plateau before it starts losing yield by over application. In cotton, it has a very narrow window between optimum rate and then too much on yield, right? So on cotton, it's going to be a different story, and we're not going to be talking about cotton here. The example is going to be corn, since there is more of this type of research on corn, and also it's easier, I guess, because it is so forgiving on the high rate side of things.
So I was trying to ask myself, did you say like the high reference, you get it by setting yourself, like putting the recommended fertilizer, or it's just like automatically and then you pass in the way to get it automatically?
So there are a few different ways of doing that. And so what I'm showing you here, this example is a farmer goes out and over applies nitrogen in one strip, right? So there is actually a physical strip on the field that they're using for reference. There are other approaches that we're actually going to be using a different approach on the exercise. And I don't remember if I have a slide for that. If I don't, we'll talk more about it when we get to the exercise. But yeah, there are alternatives to that. Okay, so now that we have a sufficiency index calculated, let's use that in an algorithm. So the algorithm I want to show you here is called the Holland-Shepard's algorithm. These are the authors of this algorithm. They're researchers out of Nebraska, where a lot of research on variable rate nutrient management has been done using sensors. And it is, so this is basically the algorithm, and I just want to walk you through a little bit of what's going on here. So NAP is basically the variable rate that is recommending for you. EONR here stands for economic optimal nitrogen rate. So this is something that if on research, we can calculate this after the fact. So let's say you go to a field, you have treatments of increasing rates. So let's say 0, 50, 100, 150, 200 pounds of nitrogen per acre. You apply those treatments in the end of the season. At the end of the season, you harvest those plots. So you know how much yield you got for each one of those rates. And normally the way that the response looks like, if you've ever looked at this type of data, is let's say if you have N rate on the x-axis and you have yield on the y-axis, yield increases normally almost linearly until a point and then reaches a plateau. So this plateau here is where we would say, oh, the optimum rate, so the rate that maximizes yield, but not more than that, was the UNR, or in the case UNR is optimizing like profit in that case, but is related also to nitrogen response and yield. It's a similar approach. However, beforehand, you're not going to know this, right? And on farmers' fields, they really don't. The best way to estimate that is by running those types of trials, which farmers normally don't do. So what would be this rate here if you're working with a producer is you go to them and you ask, what is the rate you believe is the best for a field? It's more empirical when it's actually when you're doing this on an applied sense, but it's the best we can do as far as, the growers are going to know how well their field responds to, or that field and a given crop responds to nitrogen. So this number here will definitely come from the grower as far as telling you, oh, I've used this rate in my field. This is what I believe is the best. So you start with that rate. So let's say you go to a producer, they say this is like 200 pounds of nitrogen per acre. And then you deduct any nitrogen credits. So what would be nitrogen credits? Would be anything that's bringing nitrogen already into that field. So it could be, so the variable rate component here is being in season, is at side dress, right? So it's while the crop is already, has been planted, is already growing, it's already into the season. So if that producer applied any fertilizer before that timing, so if they applied, at planting, pre-planting, near planting somewhere, that would be a nitrogen credit here. If you have irrigation and that irrigation water has nitrate in it, that would be a credit. If that corn crop is coming after a soybean season, that would be a credit. So any credit that would already be bringing nitrogen into the system will be deducted here. So this is nothing related to sensor yet, right? It's just setting the stage of how much I think I need, how much I think it's already been applied there, and taking that balance. And then the sensor data comes in. So SI is sufficiency index. So notice how this algorithm does not use straight out vegetation indices. It first normalizes them through the sufficiency index that we just talked about on the previous slide. So it normalizes that using a reference, right? And it uses that sufficiency index here, meaning that I could have any vegetation index. It could be NDVI, NDRE, green DVI, or any other many more there that exist. So it's not specific to a vegetation index because we do that normalization step. And then delta SI here is just how much we expect the crop to respond between something that received no nitrogen and full nitrogen. And we're going to see that in a moment here. So that value is fixed. So really the pieces of information we need here to create variable rate is EONR, which is like the optimum rate for that field that could be coming from the producer's knowledge. And we deduct any credits from that. And then we use the sufficiency index coming from the sensor to do that. I just want to show you this just so we talk a little bit about some of the concept behind that algorithm. So here we have different nitrogen rates going from 0 to 200 on the x-axis, and then we have sufficiency index on the y-axis. So note that this is not NDVI, it's not a vegetation index. It is the sufficiency index, which is basically has been already normalized using a reference, right? So what we see here is, so let's say when we apply no nitrogen, the sufficiency index is, in this case that we're seeing here, would be 0.7, meaning that a plot or a strip you apply no nitrogen is about 30% less in terms of a given vegetation index related to your reference. And your reference would be the one right there. Right, and it is not that it's coming a 1 from your green NDVI. It's just that because you're normalizing to a reference. So let's say the reference was like 0.6. If you do 0.6 by 0.6, that's 1, right? So that's why the sufficiency index on the top one here, the 1 would represent your reference. As you're increasing your, let's say your pre-plant side dress, or I'm sorry, your pre-plant rates, so from 0 to 50 and 100 and 150, your crop is responding positively to that. And so the rate that you apply a pre-plant at 50, in this case, kilograms of N per hectare, has a higher sufficiency index. It is closer to the reference, right? So there's less stress where you applied some nitrogen. And as you increase your pre-plant applied nitrogen rate, that stress starts to disappear until the point that is the same as the reference. So this is kind of the concept that we're going to be using, right, in this relationship. And here in this case, the delta psi is set to 0.3 because we're assuming here that if you apply no nitrogen and you apply full nitrogen, this difference here in sufficiency index is 0.3. So from 1 to 0.7. This could change depending on the field, depending on the crop, but right now we're going to assume that to be 0.3.
Sorry, so when you say it could change depending on the field, it means that if you go to another field, like how can you determine this?
So you could, so if you go to a field and you really want to calculate a delta psi that's specific to that field, all you need really is a high nitrogen reference and a 0 check. That will allow you to calculate that, because the delta psi is really the difference in SI from the high nitrogen and the no nitrogen. The 0.3 is a good starting point, but there is a problem with this if you're applying to a producer's field, because producers don't like to have a 0 check, right? I mean, sometimes they don't even like to have a high nitrogen check, and let alone a 0 check. So a producer is most likely not going to have a part of their field that they did not apply a nutrient that they know is needed. So that's why we recommend 0.3, even though that may change from field to field, but it's a good average value to plug in there.
So it means that in order to use this variable rate nitrogen application, it means that you are going to a new field. It's something that you have to apply maybe in the second season. Because how can you determine high nitrogen?
No, you can apply. So let's say if this season, if I'm planning to apply variable rate nitrogen using the way I'm showing you here, I mean, of course, first you need the equipment, right? You need to have a variable rate equipment that can do that. But as far as on the data collection and processing side, you don't need a check. You can assume it is the delta size 0.3. If the producer is willing to do a high nitrogen reference strip, that's great. If they're not willing to do it, or maybe they cannot do it, in some places, producers may be limited to the maximum rate they can apply to a field because of losses. That's the case in some places in Nebraska. I'm not sure if in Georgia we have those restrictions anywhere. But in Europe is also that way. They cannot just over apply because it's regulated. In those cases, there is a strategy to derive, to actually derive a high reference, even if you don't have a high reference in the field. We'll get to that on the exercise, but is that concept is called virtual reference, and we'll get to that, but I don't want to get into that right now. Awesome. Okay, so as I was just showing here, you know, that response of this, how the sufficiency index is changing depending on the pre-plant applied nitrogen rate and what the delta SI was right there. So the delta, I'm just going to read this out, just, you know, just so if I missed to say this before, we can just go through it. So delta psi represents how much potential room there is to catch up between the most nitrogen deficient crop, so the one that received no nitrogen, and the most nitrogen sufficient crop on that field, the one that received the highest rate. Okay, so I'm going to walk you through here the entire workflow of going from sensor data all the way to variable rate and how that happens. So it starts with a sensor, right? That sensor could be, again, a proximal active sensor like I'm showing you here. Examples of this type of sensor would be green seeker. We have the crop circle, or Optrix are also sensors, commercially available sensors that do this. It could also be any multispectral sensor mounted on a drone or on a satellite. Those sensors are collecting reflectance data for different bands, right? So I'm just representing here a few bands, being the green, the red, and the near infrared. We then combine those bands into one or more vegetation index. And again, we do that, we combine them because different bands are telling us about different characteristics of the plants and how they relate to stress. So we want to combine them to bring those different pieces of information together. And we do that by calculating a vegetation index. Then you go to the field, you're going to have a vegetation index value for your reference, but also for the part of the field that you want to apply variable rate. So we combine those two again into a different number that's called the sufficiency index. And then we plug that sufficiency index into the algorithm that we just went through, and that gives us a variable rate to be applied. So this is kind of how you would go from sensor data and how that process happens until you get to variable rate. Okay, so I have a quiz for you. So here's my question. So we go out to a field with a crop sensor and you measure green NDVI over an area that shows nitrogen deficient symptoms. And I'm giving you the field vegetation index value for that to be 0.5. You then measure green NDVI over an area that has received enough nitrogen and looks healthy. So that would be your reference vegetation index. It has a value of 0.6. Assuming an economic optimal nitrogen rate of 150 pounds of N per acre, no nitrogen credits, in a delta SI of 0.3, compute the sensor recommended nitrogen rate. I'm going to give you maybe 5 minutes here. If you want to send me your answers by email, you can do that. Do make sure that you type on the email the steps that you're doing. Don't just tell me the final nitrogen application. Show me the numbers you're plugging in so I understand what you're doing.
Can you just write in a copy and give it to me?
Yeah, if you
Excuse me, Professor.
Yes.
Yeah, sorry. As I mentioned earlier, my car broke down and I'm still on my way to campus. So can you give me a little more time? Maybe by the end of class?
Yeah, that works.
Okay, thank you.
Yeah, let me just give you 5 minutes here. Yeah, all I need is just the NF there, so the variable rate. All right, the timer is up. I'm gonna give you here a few more minutes, but we're gonna have to move on after that. All right, time is up. We're gonna have to move on. If you have not turned in yet, just, make sure you turn in by the end of the class. I'm not gonna show the answer right now since some people are still gonna have to work or to finish it, but we'll go through that next class. Okay, so last component here of our variable rate system is, so we went out to the field, we collected sensor data, we found an algorithm that could translate that sensor data to an actual rate. Now we need to implement that on the field, which means we need actual variable rate equipment, right? So I'm just showing you here one of a very quick drawing or depiction of how a system like that would work. So it does have, in this case here, in our case, it does not have sensor data. So that would be like if you were applying on the go, we would have sensor data coming right through the VR system. In our case, we have, instead of sensor data, we actually have our map that we were producing, that like we're going to do in the exercise that follows. We're going to produce the map and bring that application map into the system instead of actually having on-the-go sensing like this is showing. That system has a GPS, so it knows where it is on the field, and it just has controllers, right? So it has a tank with the product that we're applying variably in space, and it has controllers on the outlets of that, in this case of a boom, that change the flow of the different, it could be changing the flow of different nozzles or sections, but it has some control over how much is getting out, that product is getting out through the boom. And that way it knows where it is in space. It knows from the map how much should apply in different parts of the field, and it just changes that rate through the mechanics of the system to actually apply that rate that is supposed to be applied in that specific part of the field. And in the end, we get an as applied map, because one thing that we're going to talk a little bit more when it gets to the exercise is how small of an area do we want to treat variably? That's something that maybe we can be very we can think that perhaps we would like to treat every meter with a different action rate. Well, I mean, maybe we can do all the calculation for that, but when it comes to actually applying that, can our equipment handle that change from meter to meter, especially as it's moving at a given speed, right? Probably meter to meter would be too fine of a resolution for the actual equipment to adjust the rate that is changing so often, right? So that's also something that we have to keep in mind when we're making it, but just wanted to bring that up. So finally, I want to show here an example where we're combining and bringing together sensor, algorithm, and VR equipment all on the same application. So before I start here, I just want to tell you that this is a video from a non-farm study out of Nebraska, where they were using sensors to detect crop stress and apply variable rate nitrogen on the go. In this case here, they're using the Optrix sensors. You can kind of see them on that boom. So this is a high clearance applicator. This is probably corn around V12, V14. So it's pretty high, pretty tall corn that needs a high clearance applicator. You see the sensors right there. When I hit play here, you're going to see the actual applicator moving through the field, sensing the corn. There's going to be some stuff going on the top here that I'll be telling you more about as we go. So just wanted to lay that out. And this is the credit for this is Laura Thompson out of the University of Nebraska-Lincoln. She does a lot of this type of work and works a lot with on-farm experimentation up there. So I'm just going to start playing here and we'll tell you what's going on. So, the applicator starts moving. The sensors here are, they are active sensors, right? So they're emitting radiation and reading back what's coming to the sensor after it interacts with the plants. I do want to show you here what's going on first on this bottom plot here. So this is how much, so the pounds of nitrogen per acre that's being applied, and that is showing up as the black line. And this is the response you're getting across this strip, right? So it's a very long strip that's being treated on this field. So we see that So the green line there is fixed. That's the value that was set for the reference on this field. So that value is fixed across. And then the red line here is NDRE. So it's one of those vegetation indices that in that case uses the red edge band. So as NDRE is high and very close to the reference, the nitrogen rate is lower. So it's applying here between 55 to maybe like 20 pounds of N per acre, which is a pretty low rate to be sidedress. And as the sensor starts finding stress on the field, so NDRE lowers. And then, of course, I'm not showing you a sufficiency index in this plot, but always remember that sufficiency index would be the division of that vegetation index value by the reference. So when the sufficiency index lowers, since the reference is fixed, the reference value is fixed, the SI also lowers, making it apply higher nitrogen rates. So the red and black line here are kind of mirroring themselves, like, you know, one is up, the other one is low, and so forth. So we just see here across this entire strip, which I don't know how many what was the distance there, but it's a pretty long strip across an entire field, irrigated field. We're just seeing here how, if you look at the variable rate nitrogen, so the black line, how the rate was really changing across this field here. So going, changing from perhaps all the way to from 20 pounds of N per acre, all the way to 115 pounds of N per acre. And that change is coming in response to crop stress, right? So the more stressed the crop looks, the more it applies to an extent, right? Because if the crop looks extremely stressed, then applying more nitrogen is not going to help, right? It could even be just soil, bare soil. The sensor does not tell the difference between soil and plants. So if we have a very, very low value of NDRE, that could be just a patch that crop didn't emerge, you just have soil, in which case does not make sense to over apply nitrogen because there's nothing there to recover. But anyways, the overall idea is that the more stressed it is to a point, the more nitrogen applies, and the less stressed it is, the less it applies, and the more or less stressed is judged based on that reference, right? Having that reference value there is what helps us to understand how much of a level of stress there is for different parts of the field. So this is one application here that was on the go, right? So sensing and applying on the same pass. What I'm going to be showing you is not going to be that way. We're going to be using UAV imagery to do our prescription. So there's a few differences here. And one of the pros and cons that I told you in the beginning of this lecture is that the on-the-go system is a lot simpler to implement from the producer perspective, because the sensor is there, the algorithm is already in the system, it does the SI calculation by itself, it knows what's doing, it's controlling the variable rate application. So there's really very little that the producer has to do. If we're using UAV or satellite imagery for doing this, there is a lot of processing that needs to happen before you do the application. It requires more know-how and expertise in that sense, that you will be learning how to do that in the exercise. Yes.
Yeah, nowadays there is this technology of drone spray.
Mhm.
I don't know, like how my water display, maybe it's for pesticide or it's for fertilizer. So is it like doing by variable rate technology, or it's like uniform?
So that's a good question, and I actually don't know the answer to that. So the one thing I can tell you is that nitrogen is the nutrient that's most needed by plants, right? I mean, that we apply in larger quantities and volumes. So using a drone to apply nitrogen to a field is probably not going to work, because it's a lot of volume that has to be applied, and I don't think that would be the best way of doing it. I think, some of the work that other colleagues here at UGA have been doing, like Simmerwerk and his team that I know of, have been doing with using drones to apply inputs. It's from what I learned from them is that it's probably better suitable for when you have to like do spot application, right? So you go to one part of the field and apply only there, or something that you're applying at a very low rate, and that can get by with that low rate. But something like nitrogen that we apply at high rates, it's probably not a good option to go with spray drones for doing that. Awesome. Okay, so something else I want to tell you here. So this was an on-farm study that had a few different treatments. So one of them was whatever that producer was doing as their normal nitrogen management. That was one of the treatments. Another treatment was a high nitrogen reference, so just a fixed rate of high nitrogen applied throughout. And another treatment was the variable rate one, which we just saw here in action. Since this was a randomized replicated study on farm, long strips, long plots, we were able to measure, or they were able to measure yield side by side from a strip that received, in this case here is the grower. So the grower treatment, whatever that was, compared to the sensor, to the variable rate strip that used the sensor. And then because we have yield at the end of the season for both of those strips or multiple of those pair of strips, we can compare yield for that field, which is the plot that we have on top here. So the pink line is the variable rate yield across that strip. So if you go on this entire strip that we just applied nitrogen variably, when they came and harvested, that was the same strip that they were harvesting that we're showing on this data. And then the grower yield is this other greenish kind of line here. So two strips side by side, one was variable rate in space, the other was a fixed rate that the grower was their own management. What do you see there when it comes to the yield plot? What do you notice?
Variables a lot more consistent.
The variable rate is more consistent with yield. Is that what you said? Yeah, I agree, right? So if you look at it, the variable rate or the yield coming from the variable rate plots, which is the pink line, it does vary some, but it doesn't have the peaks and valleys that we see with the grower yield that is the green line, right? So it definitely, the variable rate on this field was a lot more consistent yield compared to the grower. So that's exactly it. And so this type of study here in Nebraska, I know that they've been doing the very similar study across like 60 farms. So something very, very applied, replicated multiple times across multiple locations. On average, what they found with that study is that using a sensor to apply variable rate nitrogen in corn reduced their nitrogen rates in about 30% compared to the growers' management. And most of the time, at least maintain yield. In some occasions, it lost yield compared to the growers, but most of the time, at least maintain yield compared to the grower, which in that case, if you're applying less nitrogen, especially nitrogen being one of the most expensive nutrients, and so we're applying less, investing less in that input, and you're at least keeping yield the same levels, it makes your profit goes up, right? So you're investing less money, getting the same amount of yield and profit out of it, or revenue out of it, that makes your profit go up. So this was, one thing that they found across all these on-farm studies. All right, so let's just summarize here before we get into our coding exercise. So we talked about spatial variability and why we need variable rate, especially of nitrogen in this case. We talked about the different variable rate nitrogen components, where the first one was the sensor. So we understood sensors, bands, and how plants respond to how bands respond to different plant conditions. We then talked about different algorithms, both the vegetation index specific and also a vegetation index non-specific, which was the Holland-Shepard's, which is the one that you also did the exercise on. We talked about the need for a high nitrogen reference. In this case here, I was showing you a strip that was actually that received an over application of nitrogen, and that was our high nitrogen reference, and how we use that to then calculate the sufficiency index, which is actually what goes back to the algorithm. So that's what I had today for the lecture part. So it's 10:17. Let's do this. Let me tell this first before I give you a little break here. So I did post yesterday I did a push to GitHub some data that we're going to be using today. So if you please can go ahead and download the latest version of the GitHub repository. That's going to have some files there for us. What I want to ask you to do is once you download those files, we're going to be creating a new project. I want to call that 10 sensor VRN. So please follow a similar naming scheme. So on the main folder of the course, create a project called 10 sensor VRN. I'm going to open that folder here. As you know, we're going to create the data, code, and output folders. You're going to move the partial code. It's just one script that's going to be new on the repository on the partial codes. You move that to the code folder. It's called 0426 imagery VRN partial. And on the data folder, you're going to move 3 files. 2 of them are .tiff, which are raster files, are UAV images at 2 different stages. And one of them is called plots.geojson. So that's a vector shaped file. Move those 3 into the data folder. So in the end, and then after that, of course, go ahead and create an RStudio project at the main level of this folder here, 10 sensor VRN, so we can work with that. So now it's 10:19. Let's take a break until 5-minute break in case someone needs to go to the restroom or just stand up a little. Let's come back at 10:25. So 5 minutes of break, give or take.
Excuse me, Dr. Vasquez.
Yes.
Can you go to that data file? I just want to see what's in there.
Yeah.
Thank you.
Yeah. It should be on the data folder. Is it not there?
Oh. Those 3.
Yeah, those 3 and the code. Yep.
What's the name of the project?
So the project name is 10 sensor VRN. Let me come back here. That's the name that appears on top here.
Dr. Bastos.
Yes.
So I was going to ask you really quick. I saw where you commented if I could post where I named or where I'd coded in for that zones S.
Mhm.
So that chunk, I'm looking at it now on mine, and I have like another like zone DF that I had created and I have it piped in, do I need to show you all the way up to kind of like where I first started, or like what exactly? I guess I didn't understand what you meant by, could you show me where I named it?
Well, not what you named it, but the code that created that object, I guess.
Okay, yeah, I'll get that in there. And like I said, I'm not really sure why it finally ran. Like, I don't know if you saw that. It took it like 3.5 hours to run, and it has absolutely destroyed my computer, it feels like. So I don't know what's going on.
And I think like from the plot you showed, I think I have an idea of what's going on, but I just wanted to confirm on your code. But I think I know what's going on there.
Okay, is it a simple fix? Is it something I've looked over?
It's probably one line of code. Yeah.
Wow, of course. That's about right. Okay, I'm gonna go ahead and post that real quick in this last minute.
Okay, awesome.
Thank you.
Hey, another thing, do you mind going through that Novus chunk? Because I think I emailed you about it. I have no clue how to kind of work that chunk.
Yeah, so what I want to do is actually my plan. I'm just trying to think now how we can accommodate that. So my plan was to finish this coding exercise first, which may not happen until the next class, and then like dedicate a whole class period for questions related to the final project. I know that doesn't help you right now, but what I would say, if anyone, so okay, time is up, but I just want to finish this comment here. If anyone is having issues running the ANOVAs, I mean, I want to address that in class because I think that could be confusing for a lot of people, since that's part of the code that I didn't really go into detail, as that was not the main point of the class. What I would say is, for right now, a quick way of making sure that it works, even if you don't understand what it is doing, a quick way to make sure it works is that if you look at when we did in class and you look at the column names we had then, if you make sure that your column names now are the same and match those column names, it should at least go through, right? So if you're trying to run it and it's giving you issues and you don't know how to fix it, which again is for the ANOVA code is completely understandable since we did not go into detail about that. I would just say, the first thing that I would try is just to make sure that the column names that we use in class match the column names of that you're using on that data going into that chunk for the project. Because at least if the names match, it should work. Try to do that. If that doesn't work, or for some reason, you cannot match the names for whatever reason, then maybe there's something else we have to look into that. But that would be my first thought.
All right, thank you.
Yeah, and Miller, if you try that and it's still like not working, let me know. We may do I don't know, some office, like open office hours for anyone to join to talk about that, if that is something that you and others are also running to that issue.
All right. I haven't really tried to run it just because I didn't know how to kind of adapt it to mine, but I should have pretty similar columns to you.
Yeah, as long as like, if I mean, you may, I guess the object name has to be the same coming in, and the column names should be the same as well as what we did in class. If that is the case, the code should run without too many issues. But we know with programming, any programming language, unexpected things happen all the time. So maybe it doesn't, but that would be my expectation at least. And yeah, I would just advise you to check the column names first.
All right, thank you.
Yeah. All right, so let's get started with our actual exercise where we're going to be implementing what we just learned in lecture. So if you're ready, I mean, this is how it looks like on my side, right? So I'm just gonna click on that rproj icon to launch this project and get started with that. Okay, so if you're not seeing yet your partial script, make sure you launch that by going to the our blue button, go on code, and then click on that partial script so it pops up. If you want to make sure that you're seeing the outline, you know, by this point, you probably already know how to do this, but you can toggle on and off that button right there. And I always advise you that since we're working with projects, you know, again, projects help us to keep things organized, right? So make sure you are in the right project. If you're not, even though if your script may be here, but if you're not in the right project, close this RStudio window, open the correct project and start over. Just so we know that the paths are working fine when we're importing and exporting things, and we're focused on that project as well. Okay, so here's the thoughts. What I showed you on the lecture, on that video, applying variable rate nitrogen, that was a case where we had a high clearance variable rate applicator. We had the active sensors already mounted on that applicator, so we could do sense and apply on the go on the same pass. There are a couple of potential problems with that. I mean, trade-offs, right? Everything is a trade-off. There's a couple of different problems that could happen with that compared to a UAV sensor. One of them is, for example, a producer goes, if they're doing what I just showed you, they may go into that field without really knowing how much nitrogen they need, right? Because if you think of it, if you have a field, you know the area, you're applying a fixed rate of nitrogen, you just multiply that rate by the area, you know how much you need. In this case here, the rate is changing in space. And you know, you really, before you get into the field with that system, you don't know what rates you're going to be applying. You really don't know, because the sensor is going to be sensing on the go, senses and applies right there. So you don't have a good idea of how much nitrogen you would need. That's a potential problem. Another problem is that for a producer that wants to get into this type of technology, if they want to go the way I showed you on the video, they have to invest upfront a lot of money on the sensors themselves, which may not be a best idea if they're just trying this out for the first time. So a fix for that, for both of those things, is to actually use remote sensing. It could be UAV, it could be satellite. So if you're doing this with UAV or satellite, in our case, we're going to be doing with UAV, you can actually fly that field, do all those calculations that we're going to do here, and by the end of it, you will know exactly what rate you're applying to what area, and you can calculate the total rate before that producer even goes in the field. So they have that piece of information. You know, they know how much they're applying, and also they don't have to invest upfront in a lot of sensors to be outfitted to their variable rate equipment. So it's less costly, and also they know how much nitrogen they need to have by the side of the field to make that application. So these are some of the trade-offs between going on proximal active sense and apply option compared to a passive sense then apply two passes option, right? So trade-offs there. We already talked about that the UAV or remote sensing option has a lot more processing, so there's a lot more know-how. That's a limitation of it compared to the active on-the-go application. So different trade-offs, but I just wanted to make you aware of that before we started here. Okay, so this is what happened. For that same field that we just saw that application happening, the actual application was done using the active sensor on the go, as we saw. However, the day before they applied nitrogen, they also flew a UAV, right? So they had that UAV data to compare how that recommendation would have changed if they had used UAV data instead. And that's what we're going to be playing with here. So we're going to be importing that UAV imagery, and that's going to be in the form of NDRE. Remember, NDRE is the normalized difference red edge. It's kind of like NDVI, but it swaps the red for the red edge to regain that sensitivity that the red loses under high biomass conditions. We're going to create a variable rate nitrogen grid, and we're going to talk about a little bit more about that. That's also one of the difference between using imagery or on-the-go sensing. On-the-go sensing, there's no grid. It's just sensing and applying. However, with an image, you have a whole strip that you need to break down into smaller pieces that the rate will be changing within each one of those pieces. That's why we need a variable rate grid. We're going to get to that. Then we're going to calculate all the required variables for the Holland-Shepherd's algorithm. And then create an imagery-based variable rate nitrogen prescription, export that prescription, so someone could use that. And then also validate that prescription with imagery collected after the application and see what changes happen on that field. All right, so for the setup, I left you all the packages that we're going to be using. If you just, hit play there, you may have an error. I do not remember if we already installed map tools. If it gives you an error saying you don't have map tools, you know how to fix it, go ahead and install it using the install.packages function. But if it runs through and you have already installed that, then no worries about it. Just make sure you do run that setup chunk so we have the needed packages. The first thing I want to do here is import the imagery that was collected the day before variable rate application. So the UAV imagery, we're going to call that pre-NDRE. So if we get to this chunk here, let's just read that. It is an image, it is a raster file, and we also know that because it is a .tiff file on our system. So if you go on data, it is a .tiff, that is a raster file. What function have we used in the past to import raster? Maybe we use only to export. No, I don't remember, but if you had to guess, right? So if I'm telling you that we're gonna read something in, we're gonna import something, you should be thinking that at least it starts with read, right? So read underscore something. If it is a raster, what would be your guess for what function we would use here?
Stars.
Yes, read stars, right? So remember, stars is the package that we use to read, manipulate, and export raster files. So open and close quotation marks, we're going to get outside of the code folder, inside of the data folder, and then bring in the NDRE pre-V12 TIFF. Make sure you bring the right one, not the post one, bring the pre-V12 TIFF one. Okay, I'm gonna import this, and I just want to show you something. Let's see. I don't remember now how I learned this, maybe with dimensions. Let me just try that. So this file here is, I think these are the actual dimensions of like cells and columns. It is a UAV image, meaning that we have very, very small pixel size. Pixels were about like 30 centimeter size. So it's very, very detailed imagery that we could use the way it is. However, I do want to show you here a trick to downsample that, to get less data out of it, because it is so fine, so precise, that some of the things we're going to be doing here takes a long time. And for the sake of class, I don't want you to be sitting here 10 minutes just waiting for a chunk to run. So let's just downsample that, decrease the size of that image so we work with it. And I just want to show you how we would do that. So we use a pipe here. There's a function called st_downsample. It has this argument called n. I want to say n equals 3. So I think this basically skips like one, each 3 rows, it skips one or something like that. I have to look at the documentation more closely, but it's going to basically decrease the size of this image for us. Also, I want to go ahead and just rename. So if we just print right now pre-NDRE, it has one column that has this name here, NDRE pre-v12.tiff. I want to rename that to just say NDRE to make it simpler. So after that downsample, we just add another pipe. We're going to use the function rename. We could have used also select, but I want to use rename here. I want to say NDRE equals that long name that I just copied from the print. Okay, so if we just run that and we print it, it's already on a WGS and UTM zone 14 North. So this is 14 North because this field is in Nebraska. Remember that different zones for different places in the US. I mean, in the world, but in the US here for Georgia, we have two zones, 16, 17. I think Nebraska has 14, 15, and this field is in the zone 14 north. So that's why we have a different zone for this case. Okay, so we're not plotting yet. We will be plotting here in a moment so we can see what this image looks like. But for now, we're just importing it and doing some quick on-the-go wrangling here. The next thing I want to import are the plots. So the plots object is basically a shapefile that has all the plots for this field. As again, this was an actual study that had long strips. It was a randomized replicated study that had plots. And I just want to bring the shape of those plots. So let's use the assignment symbol there. Let's import that using the read_sf, right? So this is a GeoJSON, it is a vector file. So we use read_sf to bring that. Open and close quotation marks. Let's get outside of the code folder, inside of the data folder, and then bring in the plots.geojson object. If we bring that and we print it, we can first check we can check here the first panel first. So it is WGS84 and also UTM zone 14. So it is projected already. We don't have to change that. And here are the columns that it has. So it has 13 rows, 6 columns, ID, treatment, rate, area, meter squares, area in acre, and geometry. I do want to use here a very quick function on the go wrangling here. So if we add a pipe, I want to just make the name standardized. If you remember that function clean names we're going to use, that comes from the package janitor. And because I did not load janitor up here, one way to, like, if you're just using one function of a package and you want to just like call it one time, we can call package name and then colon, and then function. So that would be clean names, right? So remember, we also use this trick here when we want to specify or be explicit about what package we want a function to come from. And we use that before using dplyr and select, because again, select is a common name across different packages. We want to make sure it's coming from dplyr. So this is just a quick trick to do that. So we run and print it. Now our columns are all lowercase. Mm-hmm. To what part? Mm-hmm. Something's different? So can I keep moving? All right. Okay. So I just want to tell you here a little bit. If we look at this treatment column, right? So this object again has 13 polygons. So it is a polygon type because it shows on the first panel when we print the plots. And if we look at the data, it has one of those plots is called reference. Then there is a whole bunch called grower and a whole bunch called sense. So these were what I was telling you earlier when I showed the video where the grower strips here were all the treatment, or is one treatment that was basically whatever that grower did for their field, that's what that treatment would be. So I'd say if the grower applied a fixed pre-plant rate and a fixed side dress rate, that's what that would be. The reference is a high nitrogen rate, in this case, 250 pounds of nitrogen per acre were applied pre-plant, and the sense are the ones that applied no nitrogen pre-plant and actually had the variable rate side dress. Those were the ones that received variable rate application on the go. And then this column here called rate pounds per acre is what was applied pre-plant at fixed rate, right? So the reference received 250, grower gave it 145, and sense strips received 0 nitrogen pre-plant. All right, so as I think it's really always important, let's do some exploratory data analysis, EDA. So the first thing I want to do here is look at the distribution of NDRE values on this image. So this is a stars object. I think I left you most of the code already. But this is a stars object that I just want to transform that to a data frame first. So if I just show you what happens here on this first couple lines, it transforms that into a data frame with X, Y, and NDRE. And then I just want to look at the distribution of NDRE for this image. So if I run that, this is what we get. We see here that NDRE values are ranging probably from very close to 0 all the way to very close to 0.4, but the majority of them are around, 0.26 probably. That would be kind of the average here of this field. This just helps us understand, if there are outliers, what is the mean of the distribution and how that looks like. So it's always good to look at distributions to troubleshoot any errors with data. Okay, so this is the distribution, right? So the density plot of the NDRE data on the image. However, it is an image, so let's map it. Let's make a plot that actually shows the image right there, right? I left you most of the code here. And I just want to walk you through what we're doing. So we're saving this ggplot to an object called pre-NDRE map. We're starting with the ggplot. We're calling geom stars. And we have to say data equals to something. So this is where you're going to help me here. So data is going to be that pre_NDRE. That was that stars object we imported. And then it's going to automatically fill the different raster cells according to the only variable that there is in that data set, which is NDRE. I'm just changing the scale field to varieties continuous. I'm changing the coordinates to equal. This is basically because if we don't have this, if you remember when we plot using geom stars, it doesn't look like a map. It's kind of like disconfigured. So chord equal makes sure that if it is in a map, the actual shape of the field, and then just changing the theme and just changing the legend position. You've seen this before. I guess maybe only the chord equal may be new, but everything else you've seen before. So just go ahead and run that, and we print it. This is what you should be seeing for this field. So the image that we're looking at right now was collected with a UAV that was using a multispectral sensor. And I think this case here was maybe MicaSense or some other camera that was multispectral. And it was around the V12 growth stage in corn. If you have not worked with corn, if you have not heard about that, V12 basically means that corn has about 12 fully developed leaves, and it's probably, I don't know, probably this high or maybe a little bit lower. But that's how high V12 corn would be, or maybe a little bit higher, depending. But so what I'm showing you here, so you went through the extra, yes. Yep. Yeah, I just changed the data, bringing in the right object. So you went through the exercise with Dr. Lacerda to basically stitch a whole bunch of UAV images. I'm kind of giving you the result of that. So I'm already giving you something that was UAV collected. You had a whole bunch of images. Those images were stitched. The bands, different bands were used to calculate NDRE, and I'm giving you this. So that would be kind of like the last steps of what, after you finish with Dr. Lacerda, this is what you would have one of those products. And that's why I also think this exercise is a good follow-up with what you just did in Dr. Lacerda's exercises, because it's a natural progression, I guess, of how we could use then UAV data for management purposes. Okay, so I also just want to quickly call map view here, right? So map view on that same object, just to create an interactive map. I don't know if I showed you this trick here. I know that in class we use code here to change the base map behind, but when you have map view, if you don't remember, because I don't remember sometimes how to specifically ask for satellite imagery on map view, If you just come here, you can just go and select S3 world imagery. That's what it would do it. So even though it's not hard coded there, but there's a quick option to do that here once you print it. So this is how the field looks like. Let me just pop this out so we can see a little bit better. So it is an irrigated field. If I turn off here the NDRE layer, of course, the background imagery here may not be for the same growing season, so we don't have to relate those two things, but I just want to show you here that this field has some different soil types, and that's what we see some of that, this sort of north-south variability. It's because of those differences in soil type. And when we bring in the imagery that we collected, we can also see those signals there, like going north-south, right? That is mostly related to soil types. However, do you see anything kind of weird about the image as far as like how things look like on the field? Any features that you're seeing in this image that you would not normally expect? Yes.
Distinct difference between like different rows.
Yeah. So we have this like east-west strips, right, across this field. That's exactly right. So this image here was collected before the side dress application. And I just showed you on the chunk above that, so each one of these strips are a different treatment. Some of them receive 250 pounds of N per acre, some receive 145, some receive 0. What we're seeing here is just differences in vigor related to those treatments, right? And this is actually what we're going to be, this stress is what we're going to be working on and trying to mitigate that stress with variable rate application. Okay, so now you're gonna help me here for us to create a map of the plots. So right now, even though we're seeing the kind of the plots on the imagery, but this is still just the TIFF, right? It's not the vector file with the plots. So let's just make a plot here to show the plots polygons. So start off with ggplot. Let's add a plus. Okay, so the plots is a vector file that we imported as an SF. Which function do we need here to show that? Sandesh, what do you think? Do that again. So if I want to show the plots here, which is an SF object, what function do we need here in this ggplot call? geom_sf, right? Yes, that's right. So we call geom_sf. You need to say data equals, and then it's just plots, right? It's just called, that's the name of the object. So if we just print that, we do see those plots right there. I do want to make one change here. So if we print plots, we have this column called TRT for treatment. I do want to have the fill of those polygons represent the different levels of treatment. So I'm going to start off here calling the AES function. What do we need to change here if I want to change the fill according to those treatments? Peter, what do you think? Say that again? To change the fill of the polygons according to the treatments on this geom_sf call. Yes, so fill, then what? Dennis, do you have any thoughts here to help Peter? What would you say fill equals to what? To show the different treatments on the, like which column here has the treatment information, the name of the treatments that we were talking about in the beginning? Say it again. Well, if we want to show the different treatments that we were talking about, TRT, right? That's where those names are. So if we just do that and then we print this, we can actually see those different strips. So that's just, let me just bring the code back again. So we just see that, so here again, on this specific case, perhaps it's not the most directly relatable commercial example for you. And the reason why is because here we actually have a study, it was on farm, but we have studies where we have strips that actually receive variable rate nutrient. If you're doing this on a farmer's field, you're not gonna have those strips, you're gonna have the whole field that you may have to break down in somehow, but you're not gonna have different treatments, right? It's just gonna be, if you think of it, the strip width should be related to the equipment swath, right? You want that to match. The length here is just basically the length of the field that we're applying. But then the different colors here, if you're doing this commercially, you're not gonna have different treatments. Basically, everything is gonna be receiving variable rate nitrogen. But because this was a study, we do have the treatments there. And the only treatments that are receiving variable rate sidedress application are the blue strips that are the sense strips. Again, the grower strips, the red strips here are just related to whatever that grower was doing on that field. That was their traditional management. The green strip that is just one there is the reference. It received a high nitrogen rate pre-plant. And then the blue ones are the only ones we're actually applying variable rate treatment. And I think that's what basically I said below here in case you need to read that later as well. So here's just another point that I guess I already made, but just to refresh that, if this producer here does not have, they have variable rate equipment, but they don't have proximal active sensors to go with that. How can we help them to still do variable rate application? Well, we can fly that field either with a drone or use satellite data instead and get this data, still have a prescription made for them like what we're going to do after. Yeah, so basically I'm just saying down there as well that because it's not on the go, we do have to partition this area into cells that each cell is going to receive a rate according to the sensor data because it's not on the go, right? So with the active sensor, it senses and changes the rate, senses, changes the rate. So there is no grid that is following, it's basically just running the field. However, when we are using UAV imagery, it cannot do that. We have to give it small polygons that is going to say, okay, this NTRE was this, efficiency index was this, that gave this X variable rate. I'm applying that rate here and changing that rate from polygon to polygon as it keeps moving through that field. So that's kind of the idea and what we're going to be doing next here. Okay, so the next immediate step here is going to be to create that grid. We're going to be doing something that involves grid creation, which you're all familiar with already, but involves some tilting of that grid, which we have not done yet. And I just want to make sure that we go through it in detail so we understand what's going on. Okay, so I'm calling this object grid VRN. I'm starting off with an object called plots. Just go ahead and add a pipe there. If you come after that second comment, let me ask someone else. What is the function that we've been using a lot to create grids? We've used this a lot when we're interpolating. We had to create an interpolation grid. We're not interpolating here, but we still need a grid. What is the function that we were using? Someone remember that?
Yes, T_make_grid.
Yes, thank you. Who was that?
Anis.
Anis. Thanks, Anis. That's exactly right. So if you don't remember the function, one way that I normally do is if I kind of know what the function is, like what the name of it is, but I don't know is exactly, I just start typing, right? So if I would say ST, and then the moment you type MA for make, it already gives you like make grid, right? So that is a way to help us remember. In the past, we did grids that were 10 by 10. So what we did here was just to say 10. However, the ST make grid function allows you to create grid cells that can have where the height can be different from the width, or the width different from the length, I guess. In that case, the only thing we have to do is provide two values. And if you remember, when we provide two values, we use the C function. So it has here this argument called cell size. We've been saying cell size equals 10 up until this point. If I want the cell size to have different dimensions, I can provide that here. So I'm providing, the first one I want to provide is 6, and the second one is 1200. Why is that? So if you think of it, 6 here, I believe was the swath of this equipment, if I'm getting it right. No, I'm sorry, that's not it. 6 here was 6 meters is how much I want to have each cell extending on length. And then the height, which normally would be the swath of your equipment, I'm just making that a huge height. And you'll understand that in a moment here, as we're going to be making things in plotting. So let's just run this right there, and let's plot this to see how that looks like. So this is how this is looking like for me. Our field is actually more like in a east-west direction, right? So the reason why I'm doing this type of grid is because I want to, let me just add another component to this plot so we can see. So let me do a geom SF data equals boundary and fill equals NA. I just want to show you what I'm trying. Oh, actually it's not boundary, sorry, it's plots. Plots is the object name. So it is a huge, and I mean, it probably didn't have to be 1200. That was an exaggeration on my side. But what I'm really trying to get is make these very small cells be cutting through the polygons that we already have. And then it can basically cut those polygons at some point on this code. So you know what, let me just change 1200 is not helping us to visualize. Let me change this to 600. That's probably a big number already. It's not gonna affect much, but this is what I'm trying to get to. It's just a grid that has very skinny and tall cells, and that it has a new cell at every 6 meters. Now, one issue that we have here, and let me decrease this even further to 300, just so we can see better this plot on the bottom. Here's one issue that you will most likely run into, when you are doing things in Georgia. So in the Midwest, this field is sort of an exception, but most fields are actually pretty squared, and they have like they all have the same size, and they all go, the producers can plant on a direction that is very like 90 degrees or 180 or whatever it is. This field here is a little bit tilted, right? And when we make a grid, the grid is not tilted, at least not the one that is created the first time. And the problem with that is if the grid is not tilted, but the field strips are tilted, meaning that the grower is planting on a tilted axis and not like a 90 degree or whatever degree that may be. It means that if we do have these cells the way they are intercepting the plots right now, the cells are not going to be following the same tiltedness, I guess, of that field or slope of that field when that grower gets to apply, variable rate nutrient. In this case, it's very subtle, right? Because the field is just slightly inclined. So it is not very clear how that could be a problem. But think of a field that's actually planted at like a 45-degree angle. The cells would be completely off those polygons, right? And we have to basically make this grid shift to have the same degree of slope as the field strips are. I know this sounds very complicated, but it's just a step we have to do to make things fit better. So to do that, we're going to use a function that only works with SP objects. If you recall from one of our first lectures, every time we use vector, we've been using vector files or vector objects in the form of SF objects. There is another package called SP, which was the first one developed to work with vector data in R. That still exists, and a lot of other packages also still use functions that need SP objects. We don't use it anymore because it's kind of being like outdated, and SF is the newer version or the newer alternative for that. However, the function we're going to use next to tilt the grid does require SP objects. So that's the next immediate step here. So go ahead and add a pipe. Let's transform this object that at this point is SF into SP. To do that, we use a function called S. And then within it, open and close quotation marks, we say spatial and with the capital first letter, like that. So if we do this, we transform this from SF to SP. So if I just print, now it's a spatial polygons, it prints differently, you can see that, and it's a different type of object. It's still vector, just a different type of object. Now that we have this in the format of SP, we can go ahead, add a pipe, and come after the next comment here. We're gonna use a function called elide, I think it's how you would pronounce that, I'm not sure. Where this function here, you give it an angle to tilt and a center point to pivot based on that center point. So that first argument here is rotate. Oh, it's not bringing up, but it is rotate. We say rotate equals a number. I played around and I just by trial and error, I was looking for an angle that would match the angle of the field. And that angle turned out to be -2.2. Maybe there is a better way, a more automatic way of finding that angle. I didn't go that route, but just wanted to let you know, I found this number here just by playing with different angles and just plotting and seeing if the angle of the grid was matching the angle of the polygons. And then it has another argument called center. So we have to give the coordinates of a center point of that field. And right now, we don't have a boundary, right? So we did not import a boundary. The only shape that we have is the plots object, which is this. So we have to do a few things to be able to give the centroid of this field as a coordinate. So we're going to start here with plots and do some wrangling on the fly. So the wrangling we're going to be doing is not going to be saved, but it's just going to be applied right here on this argument. So the first thing we have to do is use a function called ST union. That is basically going to combine all of those different polygons into one object. So if I just print this, I want to show you, now we just have one line, one big polygon instead of 13 small polygons as before. So now it's almost like it would be your boundary, even though that's kind of the idea, but it's not necessarily exactly that. Now I want to extract the centroid of that. So we add a pipe, there's a function called st_centroid to do that. If I run this, so you can see what happens, just that part, we do get now a point shapefile that is just two coordinates that are the coordinates for the center of that unionized shapefile. So it'll be somewhere here, right, that point, if we were to plot it. And then lastly, this argument here is not expecting this type of output. It actually wants just coordinates, just two numbers. So to do that, we add a pipe and add a function called st_coordinates. So if I just run this so you can see what happens, it's basically given a vector, or let me take back the word vector to not make it confusing, but it's given us two values where one is X, one is Y. This is all that this argument needs, but to get there, we needed to use some functions here in between. If we run this, we can go ahead and run it. And we can try to plot it. Let's see if that works. Yeah, okay. So it's not gonna plot yet because we have to do some more. Well, I actually already left to the code. So let's just add a pipe here after this elide. And I want to ask you for now to just comment off this last pipe so we can run until here. So we're basically transforming. So we start with plots, we make a grid based on that plot. We rotate that grid to match the rotation of the plots themselves. We transform that back to SF and we set a CRS. So if we stop right there, make sure you add a hashtag there before that pipe. If you run it and now we plot it, you can kind of see how now the grid tilted as well, right? And it tilted in because of that value that we gave it, the negative 2.2, that I would just trial and error, I found that value, but now it's tilted in a way that it matches the degree of slope, I guess, or whatever, of this field, right? So that now we can really come in and use a cookie cutter and only extract the cells within the plots and remove the cells outside of it because we don't need them. I think we can do just a couple more sentences here or a couple more lines of code and we can stop at this chunk and continue after class, on Friday. But go ahead and make sure you activate this next pipe. So now I want to crop the grid to only contain the parts that intersect the plots. To do that, we're going to use a function called st_intersection. And we need to say that we want to intersect what's coming through here with the plots object. This is how it will look like. If we run it and we make a map to see it, this is what we should be seeing at this point. So now we have those cells that we're going to be calculating a variable rate for each one of those cells. However, if you recall, we are not applying. So if this was your producer's field, you could have stopped here. This would be the grid you would use to apply variable rate, calculate variable rate. However, in this specific case, it's not a producer. I mean, it is a study on the producer's field where only some of these strips are actually receiving variable rates. So last thing we want to do here is just filter the strips that will receive variable rates. Let's go ahead and add a pipe here and come after that last comment. We're going to use a filter function where let me just print what grid VRN is until this point. So it has that treatment column there. That's coming from when we did the ST intersection. That's coming from plots. We had that treatment there. If I just want to filter the strips that are the sense strips, I just say TRT =, sense, like that. So if we go ahead and run that, and now you printed, this is what we would have. We basically only have the grid VRN cells for the sense strips, which are the ones that are receiving variable rate nitrogen only in this field. I think this is a great stopping point. Already got your attendance through the quiz. We're going to be continuing and finishing this exercise on Friday. I'm planning that for Monday, we can just have a class period to talk about the project. If anyone has questions, we can just do like a open office hours during class time. I think that's it. If you have any questions, let me know. Do remember that as you go through the project, use GitHub. That's going to ask questions and help others. That's going to be part of our grade. Make sure you do that. And I think that's all from me. See you Friday.